Good morning. Next compound is pyridine. Next heterocyclic compound is pyridine. Look at the structure. This is pyridine. Preparation. First method, distillation of coal tar. Distillation of coal tar. Second method, when a mixture of acetylene and hydrogen cyanide is passed through red hot iron tube, we get pyridine. A mixture of acetylene, CH, triple bond CH, and hydrogen cyanide, HCN, when passed through a red hot iron tube, we get pyridine. Okay? And the third method, when tetrahydrofuryl alcohol tetrahydrofuryl alcohol, sorry, the structure is tetrahydrofuryl alcohol, from furane only, tetrahydrofuryl alcohol react with ammonia in presence of Al2O3, we get pyridine. Okay, these are the three methods of preparation of pyridine. First one is distillation of coal tar. Second method, acetylene and hydrogen is passed through red hot iron tube, we get pyridine. And third method, tetrahydrofuryl alcohol react with ammonia in presence of Al2O3, we get pyridine. Next is structure, resonance structure of pyridine. Resonance structure of pyridine. Okay, look at it here. Pyridine. This pair of electron will be shifted to nitrogen. So we get a structure like this. Here it is double bond, and okay, and a pair of electron. This pair of electron is shifting to hydrogen, therefore it is getting a negative charge. And since the bond is breaking from here, this carbon is getting a positive charge. Okay. Now in the next structure, you can see that this bond is shifting to here. So we get a structure like this. N. Okay. Here is double bond, here is double bond. Since this bond is breaking from this carbon is getting a positive charge. And in the next step, you can see that this bond is shifting to here, and we get the next structure like this. Okay. And here is double bond. Since the bond is breaking from here, positive charge, of course. Okay. And in the last structure, we can see that again this pair of electron will be shifted to here. So we get back our previous structures. So here it is double bond. Okay, this is the resonance structure of pyridine. Okay, so this bond is shifting to here. So the nitrogen is getting an additional pair of electron and a negative charge. And in the final step, that pair of electron will be shifted to here, and we get the resonance structure of pyridine. Properties of pyridine. Physical properties. Pyridine is a colorless liquid having a boiling point of 115 degrees Celsius, and it has a foul smell, and of course it is a good organic solvent. So pyridine is a colorless liquid having a boiling point of 15 degrees Celsius. It is having a foul smell. Okay, now chemical properties. First one is electrophilic substitution reaction. Electrophilic substitution reaction. Like benzene, pyridine is also aromatic in nature, so it can undergo electrophilic substitution reaction. First one is nitration. When pyridine react with nitrating mixture, that means a mixture of concentrated HNO3 and concentrated H2SO4 at a high temperature, we get a compound like this. Here it is NO2. That means 1, 2, 3, 3 nitropyridine, 3 nitropyridine, 3 nitropyridine. And second reaction, sulfonation. When pyridine react with concentrated H2SO4 in presence of HgSO4 and heating, we get SO3H at the third position. That means pyridine 3 sulfonic acid. What is this one? Pyridine 3 sulfonic acid. Okay. And third reaction, halogenation. Third electrophilic substitution reaction, halogenation. That is simple. Third one, halogenation. Pyridine react with chlorine, Cl2. In presence of FeCl3, we get 3-chloropyridine. These are the major electrophilic substitution reactions of pyridine. Next is nucleophilic substitution reaction. Nucleophilic substitution reaction of pyridine. Nucleophilic substitution. Look at here. Pyridine. This is the structure of pyridine. When a nucleophile comes, this nucleophile will attack on this second position. Then what will happen? This pair of electron will be shifted to nitrogen. So we get, okay, here it is like this, okay, and here it is, since this pair of electron is shifting to nitrogen, okay, there's a pair of electron and with a negative charge, and here is our nucleophile. Now we can see that in the next stage, of course, here is a hydrogen. Hydrogen is here. In the next stage, we can see that this pair of electron will shift back. That time, hydrogen will be removed from this carbon. So we get a nucleophile will be attached to the second position. Okay, this is the mechanism of nucleophilic substitution reaction. The nucleophile is attacking on the second position. Okay, so this pair of electron is shifting to nitrogen. Nitrogen is having a pair of electron with a negative charge. Of course, the old pair of electron is here. Okay, that is understood. Okay, now in the next stage you can see that this pair of electron will go back, and that time the hydrogen H is removed from this carbon. You get nucleophile. Okay, so example for nucleophile substituent reaction with the sodamide. NaNH2, Na plus and NH2 minus. So nucleophile is NH2 minus. So what we get? Look at it here. And pyridine react with NaNH2, Na plus and NH2 minus, as we have discussed. It will attack. Okay, this can be attacked here, or when you write like this, it will attack here. Okay, or you can write like okay, here if you put the bond like this. Okay, you can put the bond anyway you can. Okay, now you are getting, okay, we get NH2. What is this one? 2-aminopyridine. 2-aminopyridine. Okay, reaction with the NaNH2. Now second example for nucleophilic substitution reaction. Reaction with the KOH. Reaction with KOH. Nucleophilic substitution, that means OH minus is coming to the ring. So pyridine react with the KOH. Okay, react with the KOH. We get, here it is OH. 2-pyridinol, which will tautomerize to give, which can be tautomerized. So it will change into, okay, 2-pyridone. It can tautomerize to 2-pyridone. Okay. And the third reaction with N-butyl lithium. Look at it here. When pyridine react with the N-butyl lithium, CH3, CH2, 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 Li, N-butyl lithium, we get, look at it here, ring, okay, we get, in the second position, what will come? This CH2, 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 CH3. Okay, so 2N-butyl lithium, 2N-butyl pyridine. We get 2 in the second position, there is N-butyl pyridine. So these are the major nucleophilic substitution reactions of pyridine. Okay, reaction with KOH. First, that means the nucleophile will come at the second position, OH. That's all. OH, 2-pyridinol, which will undergo tautomerization, 2-pyridone. Okay, reaction with N-butyl lithium. This part, the negative part, the nucleophile CH2 minus and La plus minus part will be attached to the second position. So 2N-butyl lithium. Next is reduction reactions. Reduction. First one, reduction with hydrogen in presence of nickel. Look at it here. When pyridine is reduced with hydrogen in presence of nickel, we can see that all the double bonds will become saturated. That means here you need 3 molecules of hydrogen. This bond breaks. One hydrogen here. Okay, this bond is breaking. One hydrogen here and one hydrogen. This bond also breaking, and that means we get N and one H will come. Okay. So reduction with lithium. This compound is known as pyridine. What is this one? Pyridine. We get pyridine. Then next is second one. When pyridine is reduced with Na in presence of ethanol, sodium in presence of ethanol, or LiAlH4, we get a structure like this, NH, and here is double bond. Tetrahydro 1,4-dihydropyridine. 1,4-dihydropyridine. Okay, 1,4-dihydropyridine. And the last reaction, so this is reduction. When reduced with the hydrogen in presence of nickel, we get pyridine. Second one, when you reduce with sodium in presence of ethanol or lithium aluminum hydride, we get 1,4-dihydropyridine. And the last one is ring opening reaction. Ring opening reaction. When pyridine reduced with hydrogen in presence of in presence of Hi at a high temperature, we get CH3, CH2, 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 CH3, that is pentane plus ammonia. Okay. So these are all about pyridine, and thank you.